So see, first of all, I just go with the word called dynamic. So this word is so dynamic that I can say the number of people joining itself has doubled. We have more than 100 entries. So the dictionary meaning is it is usually continuous and productive activity or change. That could be dynamic, or sometimes it's a force or a factor that controls or influences a process of growth, change, interaction, or activity. And sometimes it is testing and evaluation of a program, that is a software, by executing data in real time. So if you see all these kind of definitions, the dynamic is actually which is changing, which controls something, which influences something, and something called real time. So it has to do with a real time. So we can say that the major difference in static and dynamic is one which changes with time quickly. That is called a dynamic analysis or dynamic thing. So we can say earthquake or water hammer or relief valve discharge. These are few of the examples wherein the dynamic analysis uh, is useful. So, let's see a few of the pictures and video of the dynamics. I'll just try to share. Uh, just make sure that I'm trying to make my audio level down, probably because there is a chance that this is a voice could be a little high. So you also make sure that your voice level is low. I hope screen is visible. So these are the few pictures of actual site problems wherein the vibrations are happening. A small bore line could vibrate. Some projected areas do vibrate. Pressure control devices are vibrating. The platform itself sometimes vibrates. So these are the pictures which are more susceptible for vibration. Small bore pipings, projected piping, some of the heater piping, and these are the some failures of uh, because of vibrations. Okay, so this is a quick thing which I can show you. And one more thing I would like to show you is that uh, I think let's have this view as well. Now, this is a example of a water hammer, which also can be solved using dynamic analysis. So this is a piping system which is climbing up, and we have got the pumps. And initially the water fills up the pipe and we have to vent out the air, and that black ball was indicating till how far water has reached, like a pig. So water is climbing up and it is getting into the, say, a tank. And suppose unfortunately the pump trips, a power failure happens, then there are chances that there could be a backflow, and there could be a vacuum formation. The line can squeeze because of vacuum, and it can, because of high pressure, it can burst out. Sometimes valve gets closed and the pumps are running, so you get very high pressure peak, and because of high pressure peak, you may get some kind of failures of the elbows and bends. So this is particular phenomena is called as surge. Now definitely the software like Rover, Caesar, these are not capable of evaluating this phenomena of surge, but that is generally done by a process engineer. We believe in our company it must be done by a stress engineer itself, because he must know what is the flow and what is the pipe. So we do it ourselves. So in search analysis, we have to use another software, but the result of the search should be able to, we should be able to use into software like Caesar or Rover to perform the dynamic analysis. Unfortunately, what happens, we as a stress engineers, we are dealing with the mechanical part of the pipe, and we are most of the time ignoring the fluid part of it. Means I have been working with many of the consultants since I have started my own company, and I can see that the requirements have started becoming stringent and stringent. Like we must need a specific gap in the support. This support should not lift. If the support is lifting, if it is not taking the load, you remove it. If it is lifting more than 2 mm, if it is not required, remove it. Then the guide has to take a certain load, uh, and liberal is not allowed most of the time. So give a major amount of flexibility to the system. So as a stress engineer, you're thinking only the static part of it, the thermal part of it, and you're ignoring the dynamic part of it. Now, a simple question, if I ask those who have experience of so many years and site visit they have done, or they have addressed the site problems. Most of the problems from site are uh, the vibrations are happening, the structure is vibrating, there is a failure of a T junction after so many years. There is buckling which has happened, or some joint has failed. Those kind of problem. Have you ever heard that the plant has started and nozzle has broken, a pump is not functioning at all, the compressor has totally tripped? So these problems are not happening. The plant started leaking very immediately. So if the pump is running fine and we are struggling that the load has to be within API 2 times, not a single component should exceed more. And you are anticipating the piping which is in Caesar and 3D software is exactly at site. The friction is exactly 0.3, is exactly 0.4, and the black color which fascinates you into analysis is the same black color the system experiences, that nothing under stress. And we do the analysis. But the real problem, what site people reports to you, why it is for vibrations, then why it is for failure after so many years, or why there is something during startup, there is a problem, why they are not complaining that pump has started giving less pressure, the vessel has started overstress. It is showing me crack or something. I think it is showing my internet connection a little bit unstable. I hope it is good now. So this is because we as a stress engineer are not looking at the flow part of it. And for us, dynamic analysis is nothing but modal analysis and just skipping a frequency of 4 hertz. Now sometimes it has become 5 hertz. And we are thinking, if I keep frequency 5 hertz, then I have done the dynamic analysis, which is not the truth. So as we have seen, it is the dynamic analysis is all about the failures which you would be addressing because of the bearing failure, or some kind of cracks are getting developed into the system. So let's move forward because we have a time limitation of 1 hour today. Now let's compare the static and the dynamic load. Very simple. The static load is the one which is slowly changing or does not vary with the time. So we assume that it's a static load many a time. So static load, I can see the weight is the static load which doesn't change with the time. The thermal loads, once it is established, probably comes under static load. Dynamic loads keep on changing with respect to time. System always have time to fully react to the applied load. It means that thermal load, if you check, the temperature is changing slowly. The system is having time. It is not responding very quickly. So it's not a hammer effect which is happening. System is getting time. What you can say as quasi-static. In dynamic, what happens? System doesn't get time. So just imagine that you're standing somewhere and a small kid comes and you're unaware that he is coming. If he pushes you, you will move. Though the mass of a kid is less than half of your mass. You are weighing suppose 80 kg and kid is hardly 20 kg, still you can move. But if you know that the kid is coming and if you stand steadily, then probably he will not be able to move. Or if he starts pushing you slowly and start increasing its force, then he will not be able to push you because you have a time to respond. So response time is very much important into the dynamic analysis evaluation. In static analysis, some of the forces are zero, means what we have learned, summation fx, summation fy, summation fz, they are zero. And that is the reason when you do a dynamic analysis, you will find action and reaction. So in stress analysis, what you try to check, if you find a load onto a pump, you check the support in front of the pump, suppose a guide or a stop or a guide after the line turns, whether you are getting a opposite sign load. Then you come to know that this guide is creating me a problem, you increase the gap or you remove it. But this fundamental is not true for dynamic analysis. The sum of the forces may not be zero. If those would have been zero, the system shouldn't have been under vibration. Yeah, and that's since the forces are not zero, the sum is not zero, that's why the system is vibrating. With no unbalanced forces, the system is at rest. And due to unbalanced forces, the system is vibrating. So when the system is vibrating, just imagine that you're supposed to vibrate the system by your hand. If you're vibrating by your hand, it means that you're giving a force which is continuously changing its direction. Okay. Now the induced system reactions are equal to the applied load. Means if you apply a force of suppose 10 kg as a weight, then you will get the same reaction from the support. But in dynamic analysis, the reaction can be higher or even it could be lower. That is based on the response characteristics of the system. So sometimes you may find it is giving you a larger response, sometimes it could be lower. For example, during the earthquake, the ground floor of the structure deform in a different way and the top floor of the structure will deform in a different way, or the reaction will be shown in a different way. And that is the response. Okay, so now let's try to go next. I don't know why this the red mark has come here. Anyway, now let's try to understand dynamic loading we have now. You can see here it's a random loading. So there are various kind of dynamic loading you can check. Random in the sense you do not know what's going to happen. Like a wind, it's a random. It can change with respect to time and the magnitude could be anything. So such a kind of data has to be recorded. Earthquake, the crust of the earth releases the energy, and based on the type of soil you have, where the epicenter is, you have a primary waves, you have the secondary waves. They are also called as a Rayleigh wave and Love waves. And a wave will propagate. So the energy release could be for a certain time, but the effect of that energy could be for a longer time. And it is random. So these kind of analysis, when we do not know what earthquake is going to come in a near future. Now, recently we had an earthquake in Taiwan. So we were not knowing whether it would be 7.2 Richter scale or 7.5 or a cyclone. We do not know. So what we do in such a kind of thing, we rely on the past data, the data which we have gathered, and then we have to decide for what data we are supposed to design it. Now, it depends on the project criticality, but sometimes you can go and use the data as back as 400 years, 500 years. And there are methods for that. Okay. Now, sorry. Now, the second kind of loading is a harmonic loading. Harmonic in the sense, the load which changes with respect to time, but at the same time, we know the pattern of it. For example, the fan is making noise with certain RPM. Compressor is running with certain rotations per minute. Turbine is having certain rotations per minute. So we know that the frequencies which are getting generated, the excitations, are with respect to time, and we know that pattern very well. So when you know a pattern of the excitation, like a pulsation, the compressor vibration, turbine vibrations, those are under this. Even a flow induced vibrations, if you know the pattern of the flow, what it is happening, it can be done as a harmonic analysis. And sometimes one kind of analysis can be done as a harmonic and as good as a random. Now the random analysis, what we have seen earlier, it has got two ways of doing this, like which I was talking earlier. You can do it as a response spectrum, and you can do it as a time history as well. So response spectrum, it is nothing but you know the responses as a pre-recorded responses for different frequencies, and then you compare the system frequencies with those and try to anticipate the responses and do the analysis. And in time history, what you have, you actually know the data with respect to time, and you impose it onto the system. So the time history is nothing but, I would say, very close to the response spectrum analysis with little bit of differences into an analysis method. Now, the third kind of loading is a impulse loading. Now, impulse in the sense, if you see this, what is happening, I'll just take it a pane out of here. This is a relief valve, like a pressure cooker whistle in our kitchen. So when you cook the rice, what happens? The whistle blows up, it remains in that position for a while and it comes down. So I can say the whistle blows up, it remains with the system for a while and it comes down. So with respect to time, the load is changing. And it is coming down. So this kind of analysis is kind of a relief load analysis.